All right, hey guys, so we are going to keep on moving along in chapter 4, our chapter about transformations. And today we're going to look at congruency transformations. So let me present my screen for lesson 4.4 and we'll begin. Okay, so congruency and transformations. Congruent figures. Two figures are congruent if and only if there is a rigid motion or composition of rigid motions that maps one figure onto another. Congruent figures have the same shape and size. So since they have the same shape and size, that means that the distance is preserved and angle measure is preserved, which makes it a rigid motion or an isometry, okay? And if we perform a rigid motion or a composition of rigid motion, such as a translation, a slide, and then a reflection, or a translation and then a rotation, or some combination of those three, it's always going to produce a figure that's the same shape and size as the original. So examples down here, if a triangle is transformed by a composition of a reflection and a translation, the figure is congruent to the given triangle. So you can see here, these are not triangles, but you can see here that these four-sided figures, they look like trapezoids. They are all congruent to each other, same shape and size, so a congruency mapping occurred. Over here, the triangles are different shape or different sizes, not different shape, but different sizes, so they are not congruent to one another, so it's not a congruency transformation or mapping. Okay. Identify any congruent figures in the coordinate plane. Explain. All right, so we see that we have some triangles here. We have triangle IHJ, triangle STU. We have some four-sided figures. We have other triangles that are a little larger than the other two. So, make sure my pen's working. All right, so let's first look at triangle KLM and triangle EFG. Let's look at those for a second. So triangle KLM, that's this triangle right here. I'll kind of shade it in a little bit. This triangle right here. And triangle EFG, this triangle here. All right. They appear to be the same size. We can count units to see the side lengths. EF is 2 units long and KL is 2 units long. KM is 1, 2, 3 units long, and GE is 1, 2, 3 units long as well. All right, and the diagonals, well, we could use Pythagorean theorem to prove that they are congruent to each other, okay? And what mapping took place that would map this triangle onto this one, or vice versa? Well, it looks like they're congruent. So first I'm going to say they're congruent. And it looks like there is a reflection across the x-axis. Right? Let's see if we can come up with another example of two figures that are congruent to each other. Let me erase what I have here. Let's now look at triangle STU and triangle HIJ. So triangle STU, that's this triangle here, STU, and triangle HIJ, this triangle here. All right, again, we could count sides. JI is 2 units long and IH is 2 units long, ST is 2 units long, and TU is 2 units long, and then again, Pythagorean theorem, we could prove the hypotenuses are congruent. So side lengths appear to be or are congruent to one another. All right, so what transformation took place that would map this triangle onto that one, or vice versa, this triangle onto that one? All right, what do you think? Well, there's two that would actually work. So first we'll say they're congruent. Now, if you were thinking there was a rotation, you could rotate the triangle 180 degrees about the origin, or you could also reflect over the y equals x line, right? This diagonal line right here, that could be your line of reflection, and you could reflect over that line. So we could say we've rotated 180 degrees or reflected over the y equals x. And the last figure. So let's look at A, B, C, D, and N, P, O, R, N, P, oh, it's a Q, R, not an R, sorry, or, oh, sorry. Okay, so this little square and that one, to take a look. Do they appear congruent? They are, right? They're congruent to each other. And how would you go from this square to that one? Could you just slide to the left and then slide down? You could. How many units to the left and then down? You translate, right? Each point x comma y, translate, it maps onto x minus 2, y minus 6. Now, instead of going from this one to that one, if you were thinking I would translate to the right and then up, you could, okay, because it doesn't say which one is the image versus the pre-image. So you could say you're moving this figure 2 units to the right and 6 units up. So it could be x plus 2, y plus 6. It just depends on which one you're saying the original is. All right. Okay, so that's just some examples of looking at congruent figures in a coordinate plane. Let's keep on moving down. Another name for rigid motion or combination of rigid motions is a congruency transformation because the pre-image and image are congruent. The terms rigid motion and congruency transformations are interchangeable. All right. Describing a congruency transformation. Describe a congruency transformation that maps parallelogram ABCD to parallelogram EFGH. So first off, the way they're naming it tells you that this is the pre-image and this is the image. This is what you're starting with. This is where you're headed. This is where you're going. Okay, so that's one thing that maybe we should just write down. This is my pre-image. First one, where you start, that's your pre-image, and the second one is your image. The way they name it is super important as well because A and E have to correspond. So the coordinate of A has to map onto the coordinate of E. And that's important because that kind of helps you decide, was it simply a slide or did I have to rotate or did I have to reflect? So that's going to help you determine what kind of transformation took place. And coordinate of B and F have to match. So B is going to map to F. Now, it might be helpful to like mark it with some arcs. Let me erase these dots. So, and you don't have to mark them all, but you might want to just mark like angle A congruent to angle E. Okay, and maybe like H and D or something like that. 2 others just to kind of visually see which ones H and D I said, right? Okay, you could also mark the sides that need to match up, like side AB has to match up with side EF. So side AB has to match with EF. Okay, so that kind of helps you decide the orientation of the figure. All right. So then what I'm going to do is I'm going to try to figure out what kind of transformation took place to get from here to there. And with these, again, depending on if you're a visual learner or not, you might have to actually perform what you think happened. So for instance, to me, it looks like I may have flipped over the y-axis and then translated down. So if I flip over the y-axis, let's plot where the points would be. All right, so flipping over the y would put point A here. We'll call that A prime. Point D 2 units away, so 1, 2. D prime would be here. D prime, this is A prime. B prime, well, B is 1, 2, 3 units away, so 1, 2, 3 units away over here. That's B prime. And then C prime, we'll see is 1, 2, 3, 4 units away. So 1, 2, 3, 4 units away over here. It's C prime. right? And then if I connect them, and then what I like to also do is mark the angles. So remember, angle A had the 1 arc on it because it has to match with angle E. Angle D had 2 arcs on it because it has to match with angle H. And side AB has to correspond, has to be congruent to side FE. So now it looks like it's in the right orientation. And then I have to figure out, well, how many units do I have to slide? Well, if I move A down 1, 2, 3, 4 units, and then D down 1, 2, 3, 4 units, right? They're landing where they need to land. So it looks like I reflected over the y-axis, and then I translated each point x comma y. It translated down 4 units. So it's y minus 4. Okay, and that would be your congruency transformation. All right, let's keep on moving along. Okay, so we have 2 theorems. The first is the reflection parallel lines theorem. This theorem says that if lines K and M are parallel, so here's line K, here's line M, they're parallel to each other, they're marked with the little arrows to indicate that. If we reflect a figure over line K and then reflect it over line L, the result is really just a translation. So let's look at that. If I take segment AB and I flip it over line K, you can see where it lands, right? Here's segment A prime, B prime. A prime is the same distance away as A, and B prime are the same distance away, so it was a reflection. Then if I reflect this one over line M, this is the result, okay? But what this theorem says is if you just want to compare, so let me scribble for a second. If you just want to compare the original to the final, so ignore the middle for a second. What does it look like? The original to the final. Does it look like I could just slide it over? I don't have to do any kind of reflections. That's what this theorem says. Okay, the theorem says that if you reflect over parallel lines, then the result and the original is really just a translation. All right, so that's what that theorem says. And that's important for some problems that we're going to look at later on. Okay, so example 3, using the reflection parallel line theorem, in the diagram of reflection in line K maps segment GH to G prime H prime, as you can see, right? Here's my blue original, here's my prime after I reflected over K, and then a reflection in line M maps the prime one to the double prime one. So just like above, I'm going to flip, and then I'm going to flip again. All right, so it says, also, the distance from H to B, so from, gotta get my pen, sorry. So from here to there, that is there we go. That is 9. And the distance from D to H double prime is, oh, I did the wrong one, I'm sorry. Hold on, I was looking at the wrong one. Okay, so the distance from D to, where am I? D to H double prime. Oh, what was this? H double prime is, oh, this is a typo. I'm like, that doesn't make sense that would be 9. I was all confused for a second. That's a typo. That should be a 4. Yes, make that a 4, guys. That should be a 4. That's 4 units long, okay? So it says here, name any segments congruent to each segment HG, HB, and GA. And then does AC equal BD explain? And then what is the length of G double prime? Okay, so we have a lot to kind of figure out. So they give you this information because if from H to B is 9 units, then how long is B to H prime? It was a reflection, right? So H prime should be the same units away. So it's 9 units away. And if from D to H double prime is 4 units, then what's the distance from D to H prime? Again, if we reflect it over the line, it should be the same distance, so that's a 4 as well. All right, so if I wanted to, and I might need to, if I wanted to know the length of the entire segment, or from H to H double prime, I can now just add and get the entire length. All right, so it says, name any segments congruent to each of the following. So let's try to figure this out. All right. What segment is G, here's G, right here, G to H. What segment is G to H congruent to? Well, it's congruent to G prime, H prime, and it's congruent to G double prime, H double prime. Okay, because the segments are congruent under reflection. What about HB? What is HB congruent to? HB is congruent to H prime B. All right, and then what is segment GA congruent to? Well, from G to the line of reflection should be the same as from G prime to the line of reflection. So G prime to A. All right, so that's for part A. The next part says, let's erase all that so we have more room. Does AC equal BD? Explain. So AC from A to C, that's from here to here, is that equal to BD, the distance from here to there? So what do you think? If you're thinking yes, you are correct. All right, you can say yes, AC is equal to BD, but more importantly, why? We learned this in the last chapter. We learned that because G double prime and H double prime are perpendicular to both K and M, lines K and M, that allows us to conclude that BD and AC are opposite sides of a rectangle. All right. So BD is congruent to AC. And then finally, the last question from this part says, what is the length of G double prime? So from G to G double prime, what is the length of that segment there? So take a minute and think. Take a minute and think. Let's look at what we have above for a second, because it's going to help us. We just said from part B that from B to D, that's equal to A to C. So how long is BD? That's 13 units long, right? This is 13 units long. So if that's 13 units long, this is 13 units long. The problem is I don't know this segment length and I don't know this segment length. But isn't this segment congruent to this one, right? AG and AG prime are congruent. And isn't this segment congruent to this one, right? G prime to C is congruent to G double prime to C. And if these two segments, this one here and this one over here, if they add up to 13, aren't the outside segments also going to add up to 13, just like what is happening above? 9 and 4 also add up to 13. So the length of G double prime is going to equal 2 times 13, which is 26. All right. Okay. The next theorem says a reflection in intersecting lines. So it says if lines K and M intersect at point P, then a reflection in line K followed by a reflection in line M is the same as a rotation about point P. So it's kind of similar to what we did above, except now we have intersecting lines and we have reflections looking like a rotation. So if you look at the segment AB, it was first reflected over line K, then this A prime B prime was reflected over line M. But what this theorem says is from the original to the final, that's actually a rotation. Okay, and it's a rotation about the location where the lines intersect. So P is our center of rotation. And the angle of rotation, we're going to talk about in the next problem. Or actually, we'll talk about it a little bit here. It says the angle of rotation is 2x, where x is the measure of the acute or right angle formed by lines K and M. So whatever the angle is that's formed by the intersecting lines, we double it, and that's our degree of rotation. So in this next example, it says in the diagram, the figure is reflected in line K. The image is then reflected in line M. Describe a single transformation that maps F onto F double prime. So again, it looks like a fish or a shark of some sort. We'll call it a shark. If the shark is reflected over line K, and then that one is reflected over line M, that's what they're showing, then what it really is from the original to the new, from this one to this one, it's really a rotation. The center of rotation is where the lines intersect, so it's at point P, and the degree of rotation is going to be twice the value or twice the measure of this angle. Okay, so it's going to be 140 degrees. And that's it. All right. That's based on the theorem above. Okay, that, my friends, I think is all I was going to do. Let me just take one quick look. Yes. All right.